Hello viewers, in this module we will take a look at heteroskedasticity part 3. In the earlier modules you have had introduction and some fundamental concepts on heteroskedasticity. We will extend those in this part 3 of heteroskedasticity, and we begin with the set of tests known as the LM tests. We have already gone through some basic tests of heteroskedasticity like the Glaser test or the Goldfield-Quant test. In this module, we begin with the broader classification of LM tests in the k variable model. So, the model is y is equal to x beta plus u, and u denotes u1, u2 up to un, but variance of u is no longer equal to sigma square I. Instead, each individual ui has a separate variance sigma I square. So, that is unequal variance. Variance uj will be sigma square j, that is not equal to sigma square I. That is the basic concept of heteroskedasticity. And as you can see, this is the k variable model where x is of order n cross k. So, this is the classical linear regression model, the k variable model, and we are incorporating heteroskedasticity. Now, in the literature, there are various forms of heteroskedasticity, but the three most often or most widely used forms of heteroskedasticity are as follows. So, sigma square I is alpha 1 plus alpha 2 Z2 Z2I plus alpha 3 Z3I plus alpha p z p I. So, that tells us that sigma square I depends on other variables z, some or all of which could be the original variables x, and how many such variables are we considering? Z2, Z3 right up to Zp. So, we actually want to test the null hypothesis, that is alpha 2 equal to alpha 3 equal to alpha p is equal to 0. If we accept the null hypothesis, then we say that there is no heteroskedasticity, and the alternative hypothesis is not every alpha 2 alpha 3 alpha p is equal to 0. So, that is the null hypothesis, and the next one is the alternative hypothesis. If we reject the null hypothesis and accept the alternative hypothesis, then we say that there is some form of heteroskedasticity, and this is form A. Similarly, two other forms are form B, where we say sigma I is alpha 1 plus alpha 2 Z2I plus right through up to alpha p Zpi, and third form, often used form, is log of sigma I squared is alpha 1 plus alpha 2 Z2I right up to alpha p Zpi. So, the forms are sigma I square equal to right hand side, or B, sigma I equal to right hand side. Sometimes this is also written as modulus, because standard deviation we always take the positive value. So, some text will mention simply sigma, some will mention modulus of sigma, and the third one is log of sigma I square equal to same thing on the right hand side. Now, how do we test these? Please remember these three forms: sigma I square, sigma I positive or mod, and logarithm of sigma I square. Right hand side we have p minus 1 different z variables. So, how do we test for this? So, the LM test or LM tests. So, let us take case 1. So, the basic model is yi equal to beta 1 plus beta 2 x 2 I plus beta k x k I plus ui, and we apply ordinary least squares. That gives us beta 1 hat, beta 2 hat, right up to beta k hat. When we substitute these, we have yi hat equal to beta 1 hat plus beta 2 hat x 2 I plus beta k hat x k I, and E I is the difference between yi and y hat I. So, we apply ordinary least squares in the basic model, we find out the regression coefficients, and then the difference between observed and estimated value is the error. Now, you will have noted that forms are, specifically for form A, it is sigma I square is some function of z 2 I, z 3 I, so on and so forth. But sigma I square is not observable. So, we use the proxy E I square, and we regress E I square on a constant, say alpha 1 plus alpha 2 z 2 I plus alpha 3 z 3 I plus alpha p z p I. So, we regress E I square, what we obtained from the ordinary least squares estimate of the mother model, and we regress it on the z variables. And here this regression is known as the auxiliary regression. It is known as the auxiliary regression. And the LM test basically consists of forming the test statistic. So, the test statistic is n, the number of observations n. Remember, I running from 1 to n, I always runs from 1 to n. So, n times r square from the auxiliary regression. Which is the auxiliary regression? This is the auxiliary regression. So, from here we have to compute r square, that is defined as explained sum of squares by residual sum of squares of this auxiliary regression. So, r square of the auxiliary regression, and n times this r square from the auxiliary regression follows a chi-square with. Now, when we look at the degrees of freedom, then under the null hypothesis alpha 2, alpha 3 right up to alpha p should be equal to 0. Please remember, the null hypothesis is that each of these alpha 2, alpha 3 are all equal to 0. That means there is no heteroscedasticity. So, how many such zi's or how many such alphas do we have? P minus 1. We have p minus 1. So, this follows the chi-square with p minus 1 degrees of freedom. And we reject H naught. What is H naught? alpha 2 equal to alpha 3 equal to alpha p equal to 0 at the specified level of significance if n times r square auxiliary exceeds chi square p minus 1 critical value, which is often written as chi square A. That means, if you have a chi square distribution typically shown like this, and then to the right you have this A % probability, then if the calculated value of the statistic falls in this critical region, then we reject the null hypothesis. So, under the null hypothesis, this is the chi square distribution. So, maybe 95% of the times you want it, you would expect it to fall here. So, when it actually falls here in this region, you say that something is wrong with the null hypothesis. So, you reject the null hypothesis, otherwise you accept it. So, that is basically type A. Similarly, for type B, what we do is, again the first few steps are the same. OLS regression on the mother model to get the errors EIs, but now what we do is we regress, we now take the second form, sigma I is a function of all this, and so we regress EI on Z2, Z3 up to Zp with an intercept. We call this the auxiliary regression. We compute explained by residual sum of squares from this auxiliary regression, and the test statistic is once again n times r square auxiliary, follow the chi square with p minus 1 as usual, because 2 to p is p minus 1, and we reject this as and when it falls in the critical region. And needless to say, by now you would have anticipated that part C would be again the first are as usual, and then you do log of this. So, you have log of this, that is regressed on Z2 up to Zp, and you have once again the same method. One thing to remember is these are large sample tests. So, these are asymptotic distributions used in large samples. So, this is as far as the LM tests are concerned. Another test that is often used for heteroscedasticity is White's generalized test. So, here when we do White's generalized test of heteroscedasticity, what we do is, again what we say is y is equal to x beta plus u. This is in matrix form. So, x is n cross k. Now, here what we do is we find out the error, and that error we say, unlike earlier where we said that that error or the square of the error or the log of the square of the error, it depended on Z1, Z2, Z3 up to Zp. Here what we say is it depends on the original variables, the x variables, the squares of the x variables, the squares of the x variables, and the products of the x variables. So, the auxiliary regression that we saw for A, B and C type, that is now modified, where we regress the errors. The errors are regressed on x variables, the squares of the x variables and the products. For example, here what we have is, if for example, if we have yi equal to beta 1 plus beta 2 x 2I plus beta 3 x 3I plus ui, that is the mother regression. So, in the auxiliary regression, the regressors will be, the regressors are x2, x3, x2 square, x3 square and x2, x3. So, that will be x2I, x3I, x2I square, x3I square and x2I, x3I. This is like saying Z2, Z3, Z4, Z5. So, in this case, where EI or some function of EI is regressed on x2, x3, x2 square, x3 square, x2, x3, then n times r square of the auxiliary regression will follow a chi-square in this example with, remember, one intercept and the other z's. The z's are now replaced by these variables. So, how many do we have? 1, 2, 3, 4, 5. So, chi-square with 5 degrees of freedom. And the rule is as earlier, the computed chi-square lying in the critical region we reject, otherwise we accept. Now, another thing that we have to see is, once heteroskedasticity is detected, that means if we cannot reject the null hypothesis, then through the auxiliary regressions we have actually estimated the sigma I hats. Remember, form A was sigma I square equal to what we had written. Form B was either you write sigma I or modulus equal to, C was log of sigma I square. So, this is not White's test, this is estimation. After White's test, we are now at estimation under the general form of heteroskedasticity. So, if we cannot, and remember this was alpha 1 plus alpha 2 z 2I plus alpha p z p I. I am not writing it again because it is the same. So, I am writing just the same. So, if these are not rejected, H naught means each of these are 0. If it is not rejected, then this estimated regression will actually give us estimate of sigma I square or estimate of mod sigma I or estimate of logarithm of sigma I square. From either of these, we can obtain the estimate of sigma I square. Now, what we do is, the model was yi equal to beta 1 plus beta 2 x 2I plus up to beta k x k I plus ui, where variance of ui was equal to sigma square I, sorry, is equal to sigma square I, and we have already estimated sigma square I. So, if you divide this whole thing by sigma hat I, 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 then this becomes a new disturbance term defined as ui by, sorry, sigma hat I, and so this is giving us a close approximation to a variable which will have 0 mean because ui has 0 mean, but the variance will be sigma I square divided by sigma I square, that is equal to 1. This is sigma hat I, but it is very close. So, it is very close to 1. So, what we get is a model which is no longer exhibiting heteroskedasticity, rather this becomes the transformed model. So, this is the transformed model. So, this is the transformed model. Once again, my dear students, I repeat, If we cannot reject H naught, that means if these are statistically significant, then the final format of the estimate gives us sigma I square hat or sigma I hat or logarithm of sigma I square hat. Accordingly, we can obtain sigma I square hat, and because variance of ui is sigma I square, if we transform the model by dividing all through by sigma I hat, because sigma I is not observable, then we obtain a transformed model which has variance almost equal to 1. So, therefore, and this is called generalized least squares, but since generalized least squares would require sigma I to be known, whereas sigma I is not known, so this method of estimation is known as feasible generalized least squares. So, that is the feasible generalized least squares method of estimating the model which exhibits heteroskedasticity. Now, before ending this module, we will take a look at why we want to detect heteroskedasticity. A preliminary understanding of this has already been done in the earlier modules, but before we conclude this third part of heteroskedasticity, let us once again revisit and see how taking care of heteroskedasticity increases the efficiency of the estimate. So, for simplicity, we are considering a model without intercept, y is regressed on x, without intercept, variance is sigma I square, which is sigma square times some variable z I square. And ordinary least squares, all of us know, gives us beta plus summation ui xi divided by summation xi square, which implies that variance of beta hat is equal to summation sigma I square xi square divide summation xi square, the whole square of that, and we just substitute sigma I square as sigma square z I square. So, we get sigma square summation xi square z I square in the numerator and summation xi square whole square. So, this remains as it is, and that is the variance of the estimate of beta hat if we use the original model, ordinary least squares. Of course, this is unbiased because expectation of u will be 0, unbiased, and has this as the variance. Now, we have already taken a look at the concept of transforming the model. So, remember we had said it was a feasible generalized least square. Otherwise, supposing we had some idea about sigma square, we know what is sigma square, sigma I square. So, if we know this sigma square and this z I square, then what we can do, we can deflate the whole model by z I. So, yi divides z I is regressed on the new variable xi deflated by z I and ui itself deflated by z I. So, the variance of ui by z I will be now sigma square. So, this transformed model has become a homoskedastic model, and we will once again apply ordinary least squares, but on the transformed model. So, application of ordinary least squares on the transformed model is known as weighted least square or generalized least squares. Earlier we had seen transformation through sigma hat, that is why we called it feasible generalized least square. So, this is giving us another estimate which we are calling beta star, and so that is instead of y and x we are just deflating by z. So, we have this beta plus u by z times x by z divided by x by z whole square, summation of the product and summation of the squares. Now, this is also unbiased. So, variance will be the expectation of the square of this term, and that will give us sigma square summation xi by zi whole square divide summation xi by zi square whole square. So, this is just like sigma square divided by 1 upon summation xi square in the model where we do not have heteroskedasticity. So, the result comes out as sigma square divided by summation within brackets xi by zi whole square. Now, let us compare the variances, because both beta hat I should have written beta hat here. So, both beta hat and beta star are linear unbiased estimates, but as it will turn out, variance of beta star will be less than variance of beta hat. So, this transformed model gives us the best linear unbiased estimator. How? Because if you divide variance of beta star by variance of beta hat, that means if you have this in the numerator and this in the denominator, so 1 upon xi by zi is already there and this gets inverted. So, xi square whole square goes top and xi square times zi square comes to the bottom. Now, if you just see, this has to be less than 1 by Cauchy-Schwarz inequality. What does the Cauchy-Schwarz inequality tell us? Summation ai square times summation bi square divided by summation ai bi square has to be less than 1, where you will have noted that ai in our expression you can take it as xi zi and bi you can take it as xi divide by zi. So, ai square times bi square, sorry, I am so sorry, this is ai bi divided by summation ai square summation bi square. So, that is ai bi is xi square in the numerator, okay. ai bi square, ai bi is xi square and ai square is xi square zi square, bi is xi square divided by zi square. So, this comes directly from the Cauchy-Schwarz inequality and that gives us the basic result, that is variance of beta star has to be in general less than variance of beta hat. So, that, my dear students, concludes this module on the third part of heteroskedasticity, and this really tells us that we need to take care while estimating the model and we need to carry out tests for detecting heteroskedasticity and then we have to apply feasible generalized least squares. Thank you very much. Keep in touch, go through the study material and we will be happy to answer any questions that you have.